Hello there. Welcome back, everybody. Thank you for being here. This is the final video, the third in a series, little mini-series with some AP Calculus style problems, courtesy of University of Houston. So as usual, get yourself ready. Grab a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And I want to remind you that the point of this series is to familiarize you a little bit with Desmos. You should expect the questions to be harder on your AP exam now that you're given the capabilities of Desmos. But this is also to reinforce some of the fundamentals and how you would set up a problem on the AP Calculus exam. Even if it's a tougher question, they'll be using some of the same phrases, and so the setup and the process will largely be very similar, even though these problems provided by the University of Houston are quite a bit easier in general. Now this problem does have 4 parts to it, so I would like you to do it in about 12 minutes if possible. Part C is going to take a little bit of time, and Part D is also going to take a little bit of time, but now that we have Desmos, Part D would actually take nearly no time to represent. I might blab a little bit about what's going on there mathematically. And when you're ready, come on back. Join us. See how it's done here. Okay, let's get started. So we have a particle that's moving along the x-axis so that its acceleration is given by this equation. Now, acceleration is the derivative of velocity. At time t equals 1, the velocity is v1 equals 8, so that's giving you an initial condition. We have the derivative of the velocity and an initial condition of the velocity. So that's going to help us solve for the velocity equation. They also give us the position at time 1 is 10. This is also another initial condition. Remember that velocity is the derivative of position. So they're giving you another initial condition, and we're going to have to use that in part C. Let's begin with part A. Now, when they give you a derivative and an initial condition, 9 times out of 10, they're going to have you solve the differential equation. Even if it doesn't say dy dx or dy dt, you know that the acceleration is the derivative of the velocity. This is dv dt. So if we write an expression for the velocity, we're going to use the Fundamental Theorem of Calculus. It says that the change in velocity overall from 1 to t is the same as the integral of its derivative, which is a of t dt. So v of t is equal to this integral of 24t minus 12, and then plus 8, because we add the initial condition on the other side, v1, and we're given that that is 8. Now, this derivative, or rather antiderivative, is very easy. And the fact that it goes from 1 to t makes it even easier, because this is going to be 12t squared. Of course, the t just keeps those things plugged in. And then we're going to subtract. If you plug in a 1, you just get 12 times 1 squared. That's 12. Minus 12 times 1, still 12. And then we're adding 8. So the velocity equation is given by this quadratic. 12t squared minus 12t plus 8. I know I did a weird kind of right to left thing. Easy peasy. Super easy. Now let's look at part B. Yes, part B. Part B says, at what values of t does the particle change direction? So we're looking for values, whereas last time we were looking for an expression, like an equation. Now we're looking for values of t where the particle changes direction. What does that mean exactly? Well, that means that the velocity goes from positive to negative, or negative to positive. So I'm going to write this like that. because I am a math person, so I am lazy. But it makes perfect sense, right? Velocity changes sign. You could also write the velocity changes sign, but I prefer to write it like this. So let's make sure that this even changes sign. Does this even hit 0? I don't know. Does it hit 0? Let's factor out a 4. So this turns into 3t squared minus 3t plus 2. We could, of course, also just put it on Desmos, but I want you to be competent in basic algebra skills. How do we tell if this ever even hits 0? We use the discriminant. And that's going to be equal to 9 minus 4 times 3 times 2. Oh, buddy. This is less than 0, which means this doesn't even hit the x-axis at all. It never hits 0, so it never changes direction. It's always going forward. So particle never changes direction. And the reason is because v of t is always greater than 0. It never hits 0. We determined that from the discriminant, that this quadratic function is never equal to 0. It has imaginary solutions. So we can say that for no value of t, never changes direction. Okay, very good, very easy. Part C. Part C says to write an expression for the position, so we're going to simulate the exact process that we did for part A, except now that we know what v of t is, we're going to say that x of t minus x of 1. So the overall change in the position from 1 to t is the integral from 1 to t of its derivative, which is the velocity. And we're given this initial condition, so x of t is equal to the integral from 1 to t of our velocity. That's 12t squared minus 12t plus 8 dt. And then we're adding x of 1 on the other side, which is our initial condition of 10. So again, we can power rule this quite easily, guys. This is cake. It's light work. Child's play, one might call it. Okay, we're going to evaluate this from 1 to t. And then we're going to add 10. So let's just be careful. Of course, if we plug in t, no surprise, just stays virtually the same. But if we plug in 1, we've got to be a little bit careful. This is going to be 4 times 1 cubed, 4, minus 6 times 1 squared, 6, plus 8 times 1, and then plus 10. So this is negative 2 plus 6, or I guess I should just say negative 2 plus 8, which is just 6, plus 10. So altogether we have that x of t is equal to 4t cubed minus 6t squared plus 8t plus 4. All right, that is part C. Took a little more time there, right? We had to plug in 1, evaluate that, but not too bad. So for part D, find the total distance traveled from 1 to 4. Now we have to be careful on how we understand total distance, and this problem actually ends up being a lot easier than I thought because we don't have to consider too much. For total distance traveled, where should I put this? Where's clever? Total distance means that even if the velocity is negative, I don't want to count it as opposite, like in displacement. If you go forwards and then you go backwards, the displacement is going to cancel those segments out. No, total distance should consider all of the segments. So the total distance is going to be the integral of the absolute value of the velocity, which just says, let's make all the velocities non-negative. Let's make them positive if they're negative. And then we can add them all up like that, and that'll give me the total distance. It won't count any of the backwards motion as negative. So we're going to do that, but fortunately, we found out that v of t is always positive. So the total distance really just is in this case, is just the integral from 1 to 4 of v of t dt, which is simply x of 4 minus x of 1, and we already know that x of 1 is 10. So we can just say this is, let's plug in 4. 4 times 4 cubed minus, what was the function for x? 6 times 4 squared. 8 times 4. Yeah. Plus 4. And then minus the initial condition of 10. So, I guess it is a little bit of work in it. Well, let's see. This should just be 128 plus 32 minus 6. I believe it should just be 154. I mean, we can check this on Desmos, of course. Let's plug this in. So if we have 4x cubed, minus 6x squared plus 8x plus 4, and we turn this into a table, we can simply plug in, what are we plugging in here? 4. 196. And then if we plug in 1, 10, oh, so maybe it's a good thing that I checked this. It's a very good thing that I checked this. This is 256 and this is 96. Got it. Which is significantly different. So we're going to have, let's see, minus 100 and plus 4. Looks a little bit better. 192 minus 6 is going to be 186. Okay, and that's what we would get if we did 196 minus 10. Yeah. All right, so we used Desmos at the end there, but really we didn't need that for that much. And this is the total distance traveled by the particle from 1 to 4. So in general, we have to take the absolute value, and I would have just done this. Might as well show you here. I would have just done integral from 1 to 4, and then I would have used the absolute value function of whatever the v of t was. Yeah, would have done something like that. So v of x would have been, of course, 12x squared minus 12x plus 8, and there we have it, right? In this case, it's the same as not having the absolute value because our function was only ever positive. But if we had a velocity function which could be negative at some points, we would have to be careful by putting the absolute value. Yeah, like that. Okay, so that's how we use Desmos to speed up our processes. It's not required. I did most of this by hand, you'll notice. And then we did use this algebra 2 fact or algebra 1 fact that checking with the discriminant gives us the conclusion that this velocity will never be 0. Therefore, the particle never changes direction. Bit of a trick question there. Okay, I hope you were able to finish that in about 12 to 15 minutes time on your own. Part D was shorter than I thought, so yeah. That's enough blab out of me. I'll see you guys next time. I hope you enjoyed this mini-series courtesy of the University of Houston, for which the link to these questions will be in the description of the video. See you next time.